So let's talk a little bit more about the substituent effects. So if you have methoxy, hydroxy, and amine substituents, we're going to talk briefly about these, especially the hydroxy. So if you have methoxy or hydroxy and amine substituents, those are very strongly activating groups. And if you do a halogenation, even without the Lewis acid catalyst, okay, you actually get multiple halogenation. So notice that there's no Lewis acid. That's usually the FeVr3, the catalyst. So if you just place that in water, you will be in for a big surprise. What happens is the bromine is going to you will have multiple halogenation. So, and you should know why I place them in these positions, because once again, this is orthopara directing. So that's what you would get. And that's actually very bad. It's not a good reaction. Let me just fix the directing here. Orthopair, we'll just leave it at orthopair. Now, there's a solution to that, and is that if you want to monohalogenate rather than polyhalogenate, what you can do is you can run it in a nonpolar solvent, which is carbon tetrachloride. Water was a polar solvent. And at 0 degrees Celsius. So you would get then the ortho, and you would get the para. So this is a much more useful reaction. Now with the amines, it's even worse. I mean, it's just, if we look here, amine is an even more strongly activating group than the OH and the OR. So you would get, even if it's at 0 degrees Celsius, once again, this is orthopara, you would get the polyhalogenation here. And also this is bad. Now, I'm not going to go over the solution for this because the solution is quite involved, and that will be done in chapter 22. We will get to mention that in chapter 22. Now, the next section is about also facing other limitations here, but we have solutions for them. We always think about problem solving in organic chemistry. So if you have Friedel-Crafts alkylation and acylation, so if you have a Friedel-Crafts alkylation with benzene, you might get, or you will get, a polyalkylation, meaning you will have enough of this alkyl group, alkyl chloride, in this case ethyl chloride, to actually form this. And again, this is not good. So you can have ortho, tri-substituted, even tetra-substituted, meaning you add 4 of these groups. So the solution to this is to simply add more benzene. Is use excess benzene so that you would have enough benzene to react with these ethyl chloride groups. Once again, the reason why is because these are activating groups. So it's more reactive than actually the benzene groups, right? So if you have this first, let me show you this. This is more reactive than benzene. So guess what? It's going to outcompete the benzene to get that other group attached there, and then there, and afterward. So that's the problem that we're facing here. However, there's no problem with polyacylation because of a very simple fact. So if we add this, we don't get more acyl groups added for a very simple reason, is that this is a deactivating group. So the benzene is even more reactive than this. So you're just going to, it's not going to compete with benzene at all. So there's no problem with that. The next one is a very, very important, is that deactivated meta-directing benzene derivatives and aniline or aniline derivatives give poor yields of Friedel-Crafts products and should not be used in the reaction. All of these, as you know, these are all deactivated meta directors, and they cannot undergo Friedel-Crafts reactions. So, you know, all of these are deactivating groups, strongly deactivating groups. Now, aniline is a different issue. So let's talk about aniline. What makes aniline? You say, okay, well, that's not actually a deactivating group. It is not. So once again, if we go back and look here, amine on aniline is a strongly activating. So what is happening here? How come that's lumped in with those other ones? And the answer is quite it's quite straightforward. Is that aniline has the amine group, which is an electron donating group, and what's going to happen is that when you add the Friedel-Crafts, so, and one of them is the catalyst, AlCl3, the amine group is going to react with the aluminum chloride. So this was strongly activated before you engage in the reaction. What's going to happen is instead of having if you recall from before, the aluminum chloride would react with the alkyl chloride, etc., or the acyl chloride. Here you're dealing with actually this reacting with the aluminum chloride. So I'm going to, before I show you that, I'm going to explain a little bit here, because you might be saying, what is he talking about? But let's show you that. So here it is. So we have, here's the NH2. And when you have this right here, actually, let's show you this. So if I have, let's say, Friedel-Crafts, if I have CH3, CH2, Cl, and then here is the AlCl3, if you recall the mechanisms, that's why mechanisms are important. So you're thinking, okay, yeah, this is going to go there. Nope, this is going to go there now instead of this. Simply amine in this case it's more basic, would act as a stronger Lewis base. So instead of the reaction going between the ethyl chloride, let's say, and the aluminum chloride, is going to go between the amine group and the aluminum chloride. And guess what happens? This is what you're going to get. And things have to make sense in this class. I always say this to students is try to understand rather than just memorize. If you look here, this is negative and this is a positive. And the question is then, oh, what happened? What has become of this group right here? It's an N with 3 bonds and there's a positive charge. Well, let's go and look at an N with 3 bonds and a positive charge. What has it become? Strongly deactivating. So that's the explanation that is used here. So this becomes a strongly deactivated, and meta-directing. Okay, so that's it for this lecture. So we're going to stop here. For the next lecture, it will be from this page, from the reactions of substituents on benzene to synthesis.